Hello, everyone. I'm Cheng. Today, I'm going to do the final presentation on my project, Automatical Wireless Network Data Collection. Recent years have witnessed rapid deployments of wireless mesh networks. For example, industrial IoT networks will contribute up to $47 trillion in added value globally by 2025. Industrial wireless mesh networks typically connect sensors, actuators, and controllers in industrial facilities such as steel mills, oil refineries, and chemical plants. Over the past decade, a large number of IEEE 802.15.4 based wireless networks that implement wireless HAT and RSA 100 standards have been deployed in real-world industrial facilities. The wireless network's communication data, which describes the states, performance, and the dynamics of the wireless networks, plays an important role in improving the network configuration, providing moderating data for simulation, and analyzing the network. However, collecting such data is a complex and time-consuming task because the engineers have to generate various combinations of parameters, run these configurations on the network, and wait to collect the data. Therefore, the goal of my project is to collect the wireless network communication data automatically. Next, let me introduce the design of my project. I will deploy my project on a wireless HAT network. First, the network manager of the wireless HAT network generates the routes and transmission schedule for all network nodes. It will traverse various combinations of multiple network configuration parameters and generate different routes and transmission schedule accordingly. Then it allocates the routes and the transmission schedule to each network node. All nodes will transmit data packets according to the routes and the transmission schedule and the various configurations one by one. Then, when the network is running according to the routes and the transmission schedule generated by the network manager automatically, the listener will listen to the communication activities of each node and record them. In the end, the collector will collect the records from all network nodes, pre-process the records, and copy them to a server. Therefore, after running this automatic wireless network collection service, the researchers can collect the communication data that they need and the various network configurations without the need to configure the network manually, waiting long time for the data collection and store the records manually. I run the implementation of my project on a network that consists of 50 nodes, which are located within different rooms in an office building. The left figure shows the deployment of the network. Each node is composed of a telespeed device, a Raspberry Pi 3, and a battery box, as the right figure shows. The network manager and the collector run on a server, which is the desktop located remotely from the wireless network. I adopt the implementation provided by researchers at Washington University in St. Louis to build the wireless HAT network. The server runs on a Linux system provided by Ubuntu, while each telespeed device runs on TinyOS operating system. I have used the C and C++ to develop the program of the network manager, developed the listener by using NetC language, and used Java to complete the development of the collector. The following are the sample codes of the TinyOS implementation that runs on a telespeed. Next, let me run the project on the remote test bed. First, let me log in the remote server. Now we log in the server. Let me start the program. the program will first generate the routes and the transmission schedule. Then it will send the transmission schedule and routes to each node. For example, the node 147 is scheduled to transmit a packet to node 146 on channel 2020 in the third time slot. Now all nodes are waiting for the synchronization before the communication. We can take a look at the code. These are the TinyOS codes for wireless communication. First, it defines the parameters for wireless communication. Then it defines a timer to start the node operation. A node will start operating after a synchronization window. Then it will use a timer to search the next scheduled time slot to start transmitting data. In the scheduled time slot, it will set up the physical channel, perform sending or receiving according to the transmission schedule. Now all nodes are waiting to complete the synchronization. The program prints the communication activity of each node. Finally, the communication activity will be copied and stored in a text file. Let us take a look. Like this. That's all my presentation today. Thank you, everyone.